Picture this. You're watching a steaming cup of coffee sitting on your table. Within minutes, the steam stops rising, the liquid cools down, and you're left with lukewarm, lifeless coffee. Now tell me, have you ever seen the opposite happen? A cold cup of coffee suddenly start bubbling and releasing steam on its own? Of course not. But why? The answer to this seemingly simple question will lead us to one of the most profound discoveries in modern science, and it might completely change how you see time, the universe, and even your own existence. The word entropy sounds intimidating, doesn't it? Like some term invented by scientists just to confuse us even more. But what hides behind this mysterious name is something surprisingly elegant and even poetic. Entropy isn't some supernatural force or invisible particle wandering through space. It's something far more subtle and yet revolutionary, an ingenious way of counting possibilities. Think about your sock drawer. When you organize it perfectly, with every pair folded and aligned, there's only one way for it to be organized. But how many different ways can it be messy? Hundreds, maybe thousands. Entropy works exactly like this. It measures how many different ways a system can arrange itself internally without you noticing any difference from the outside. To understand this better, imagine you have fantastic microscopic vision and can see every atom in your coffee. What you see from the outside is simple. A brown liquid, still, lukewarm. But inside, trillions of molecules are dancing a frenzied dance, colliding, spinning, vibrating. There are trillions upon trillions of different ways these molecules can organize themselves and still produce exactly the same lukewarm coffee you observe. This is entropy's secret. It doesn't measure messiness in the common sense of the word. It measures multiplicity. How many different microscopic stories can tell the same macroscopic story? And here's the crucial point. The more possible stories, the higher the entropy. It's as if the universe were an obsessive accountant, always keeping track of every possibility. Now, let's do a thought experiment that will clarify all of this in a way you'll never forget. Imagine a chessboard, but instead of pieces, you have 64 coins. Each coin has a blue side and a red side. When all coins show blue, you have a unique configuration. There's only one way for all coins to be blue. The entropy here is minimal, almost zero. But what if you flip just one coin to red? How many different configurations does that allow? Exactly 64. One for each position where that single red coin could be. That's already quite an increase, isn't it? Now imagine you have 10 red coins and 54 blue ones. The number of possible arrangements explodes to over 150 million. And when you reach the middle ground, with 32 coins of each color, the number of possible configurations is so gigantic we can barely visualize it. This coin example reveals something fundamental about how the universe works. The middle ground states, those that seem more balanced or normal, aren't special because someone planned them that way. They're more common simply because there are vastly more ways to reach them. It's pure statistics, but statistics on a scale that transforms quantity into quality. This is where Ludwig Boltzmann's genius comes in. An Austrian physicist who had one of the most brilliant ideas in all of science history. He realized he could connect this microscopic world of possibilities with the macroscopic world we experience through a formula. S equals K times log of W. Don't be scared by the symbols. The idea behind them is beautiful. The S represents entropy. K is just a constant, named after Boltzmann himself. And W is the number of microstates, that is, all those possible microscopic configurations we talked about. The logarithm serves to transform gigantic numbers into something more manageable, and also ensures that when we combine two systems, the entropies add up instead of multiply, which makes much more physical sense. This formula is so important, it's engraved on Boltzmann's tombstone. And for good reason. It gave us a new way to understand why things happen the way they do. Not because there's some mysterious force pushing everything toward disorder, but because, statistically speaking, the most probable states are those with more ways to exist. This leads us to a fascinating insight about the nature of time. In the most fundamental physics, the laws governing individual particles are like movies that can be played forward or backward. Both directions make perfect sense. If you filmed two billiard balls colliding and then played the film in reverse, it would still seem perfectly plausible. This is what we call time reversibility. But in the real world, things clearly have a preferred direction. Eggs break but don't reconstruct themselves. Perfumes spread but don't reconcentrate. People age but don't grow younger. This temporal asymmetry we experience every day doesn't come from any fundamental law forbidding reversal. It emerges naturally when you bring together billions and billions of interacting particles. Think of it this way. Imagine you have a box divided in half, with all gas molecules concentrated on one side. This represents a low entropy state. There are relatively few ways for all molecules to be squeezed into just half the available space. Now, remove the divider. What happens? The gas expands to occupy the entire box, because there are enormously more ways for molecules to spread throughout the whole space. Theoretically, the molecules could, by chance, regroup all in one corner of the box again. The laws of physics don't forbid this. But the probability is so absurdly small, it would be like winning the lottery every day for 1 trillion consecutive years. In practice, it's impossible. This is where we encounter the second law of thermodynamics, one of nature's most fundamental laws. It states that the entropy of an isolated system never spontaneously decreases. In other words, the universe has a preferred direction, and that direction always points towards states with more possibilities, more multiplicity, more entropy. But here's what's truly fascinating. This law isn't some authoritarian imposition by the universe. It's a natural and inevitable consequence of probability mathematics applied to systems with many parts. It's as if the cosmos were a gigantic casino where the odds always favor the house, and the house in this case is increasing entropy. Let's make this even more concrete. Imagine two connected containers, one with many red balls and few blue ones, another with many blue balls and few red ones. If you shake the system, allowing the balls to move freely between containers, what happens? Gradually, you'll find a more balanced distribution, half red and half blue in each container. This doesn't happen because the balls want to balance out. It happens because there are enormously more ways to organize the balls in a balanced way than in an unbalanced way. The system simply explores all available possibilities, and the overwhelming majority of these possibilities lead to equilibrium. This process of constantly searching for the most probable states is what creates our experience of time's passage. When we see a window break, we're witnessing a system moving from a state with relatively few possible configurations, intact glass, to a state with enormously more possible configurations, scattered shards. Entropy increases, and with it, our sense that time has moved forward. What's interesting is that this arrow of time isn't written into any fundamental law of physics. It emerges naturally from the collective behavior of systems with many parts. It's an emergent phenomenon, something that arises when you bring together many simple elements, even though those individual elements have no temporal preference. Think about the difference between a single water molecule and an ocean. An individual molecule simply vibrates and moves according to reversible microscopic laws. But an ocean can have tides, currents, storms, complex behaviors that emerge from the interaction of trillions of molecules. The arrow of time is similar. It emerges when you have macroscopic systems with enormous numbers of possible microstates. This gives us an almost poetic perspective on our existence. We are conscious beings navigating a universe that is constantly exploring its possibilities, constantly evolving towards states with greater multiplicity. Our ability to remember the past but not the future, our experience of cause and effect, our own mortality, all of this is intimately connected with entropy's inexorable growth. But here's something that might seem paradoxical. Although entropy always increases globally, locally there can be islands of increasing order. Life is a perfect example of this. Living organisms manage to create and maintain highly organized structures, apparently defying the general tendency toward disorder. How is this possible? The answer lies in the fact that living beings aren't isolated systems. They constantly exchange energy and matter with their surrounding environment. A plant can grow and organize itself by capturing solar energy and organizing molecules from air and soil. But in the process, it increases the environment's entropy more than it decreases its own internal entropy. The total balance still favors entropy growth. It's as if life were a kind of cosmic surfer, taking advantage of entropy's inexorable flow to create temporary pockets of order and complexity. We humans are perhaps the most sophisticated example of this phenomenon, complex and organized structures that exist precisely because the universe is constantly increasing its total entropy. This perspective gives us a unique view of our place in the cosmos. We're not passive observers of a deterministic universe. We're active participants in a cosmic process of exploring possibilities. Every thought we have, every decision we make, every word we speak is contributing to the universe's total entropy increase, but in a way that allows the emergence of consciousness, creativity, and meaning. When we look at the night sky and contemplate the cosmos's vastness, we're seeing entropy in action on an unimaginable scale. Stars are born, shine, and die, scattering heavy elements through space. Galaxies form, evolve, and eventually disperse. The universe itself expands, cools, and evolves toward a state of maximum entropy that scientists call heat death. But even this apparently grim perspective has its beauty. The fact that we're here, conscious and capable of contemplating our own existence, is testimony to the incredible creativity that can emerge from the apparently simple process of increasing entropy. We are, literally, the universe getting to know itself. Entropy, therefore, isn't just an abstract physics concept. It's a key to understanding our own temporal nature, our mortality, our capacity to create meaning in a constantly changing universe. It's the reason we can have memories, make plans, learn from the past, and imagine the future. And perhaps this is why the concept of entropy resonates so deeply with us when we truly understand it. It's not just a mathematical formula. It's a poetic description of how reality unfolds, moment by moment, possibility by possibility. It's the silent music that accompanies our journey through time and space. So the next time you see a cup of coffee cooling down, remember? You're witnessing entropy in action. You're seeing the universe explore its possibilities, following the statistically most probable path toward states with greater multiplicity. And you, as a conscious observer of this process, are an integral part of this cosmic dance between order and possibility. Entropy teaches us that time isn't just an abstract dimension, but an emergent experience that arises from the collective behavior of complex systems. It shows us that our conscious existence isn't an accident, but a natural and perhaps inevitable consequence of a universe that is constantly exploring new ways of being. And with this understanding, perhaps we can find a different kind of meaning in our brief passage through this constantly transforming cosmos. Not a meaning imposed from outside, but a meaning that emerges naturally from reality's very structure. A meaning that is, simultaneously, deeply personal and cosmically universal. Because knowledge is just the beginning.